Hello geometry classes, welcome back to another exciting video. Today we're going to talk about section 8.2.2, how does the area change, part 2. In the last section we talked about how area of similar shapes was related to the ratio of their side lengths, and the ratio of their side lengths was also called the zoom factor or the linear scale factor. Today, we're going to review that a little bit, but we're also going to see how perimeter of similar shapes is related to the zoom factor and how it's related to the area factor, okay? So, to begin with this, in the last chapter, or in the last video, we had a zoom factor. Now, you're very familiar with zoom factor. You've worked with it a lot before. So this should be nothing new. Zoom factor. Now the zoom factor can also be called the linear scale factor. Don't forget that. We also talked about the area factor. Okay? So we talked about the area factor. Area factor. All right. So what we want to take away from this, there is a relationship between these two things. The zoom factor is denoted as R, okay? If you know what the zoom factor is, it is represented by R, okay? So, for example, if you said that the zoom factor was 5, R equals 5. Zoom factor is 10. R equals 10. The area factor, on the other hand, that's going to be related with R squared, okay? R squared. So, you have R for the zoom factor, you have R squared for the area factor. So let me just give you a few of these, okay? Let's say R was 2. Let's say R was 2, okay? The area factor would then be 2 squared or 4. If the zoom factor was 3, it would be 3 squared or 9. 4 squared or 16. 5 squared or 25. So on and so forth. You know, you can do this forever, okay? Whatever the zoom factor is, if you square that number, you will end up with the area factor. And remember, the area factor is what you multiply by to get a larger similar shape or a smaller similar shape, okay? Same thing with the zoom factor. It's what you multiply by to either get a bigger shape or a smaller shape for their side lengths, okay? So zoom factor is for side lengths, area factor is for the area. Both of them are numbers and ratios that you multiply by to change from similar shape to similar shape. Okay, to give you an example here, let's say, and I'm going to erase part of this table to make some room. Let's say we have two shapes, okay? Let's say we have two shapes. And I'll try a different color here. Let's try purple. Let's say we have two shapes like this. We have one shape and we have another larger shape. Now, you can see that these are two separate shapes. If I told you the dimensions were 3 and 4, 9 and 12, you would ultimately be able to realize that yes, these are similar shapes. They have a zoom factor of 3. Why? Because 9 divided by 3 is 3, okay? 12 divided by 4 is 3. Their zoom factor is 3. Therefore, their area factor is 9, okay? Now let's test this. the area of this rectangle, the small rectangle, is 3 times 4, right? So the area equals length times width equals 3 times 4 equals 12. So we know that the area of this is 12. Now, if I check the area of the larger shape, I can find that out as well. So area equals length times width equals 9 times 12, which equals 108. Okay, so we now know these two numbers. If I go back and check to see if this is correct, I can check it this way. I know the area of the smaller shape. Over here, it's 12. I know that the zoom factor was 3. So I know the area is 12. I know the zoom factor was 3. Can I find the area factor, the number that I multiply by, to get the new area? Yes, I can. The way you do that is you take the area of the smaller figure. So you take the area of the smaller figure and you multiply it by the area factor. In this case, the area factor is 9 because our zoom factor is 3, right? So 12 times 9 equals 108, which is what we got for our area. So as you can see, the zoom factor and the area factor are related. The zoom factor is found by comparing the ratios of the sides, and the area factor is found by squaring that ratio of the sides. Okay? This is very important for all similar shapes. All similar shapes. And just in case anyone is confused, this 12 is the area of the small figure times the area factor. Area factor. And the area factor is found from the ratio, which was 9 divided by 3 is 3, and 12 divided by 4 is 3. Okay, so that's a quick review on how zoom factor and area factor are related. Let's go ahead and take a look at perimeter. Okay, so we're going to continue by taking a look at area. We're going to continue by taking a look at perimeter and how it relates to the ratio of the sides of the shape. So let's take a look at this table. Now in the previous problem, we had two shapes. We had a shape that was like this, with 3 and 4 and 9 and 12. It's the exact same shape we just used as an example, except now we're going to take out and look at more dimensions. So let's go ahead and finish off these shapes. Because they're rectangles, we know the opposite sides are exactly the same. Just like this. Now, if I'm getting the ratio of the sides, once again, the ratio of the sides is the zoom factor. It is the zoom factor. So, to make a ratio, one number divided by another, we take this divided by the corresponding side, this, to get a ratio. Because they're similar, all the zoom factors are the same. So 9 divided by 3 equals 3. We already know that these shapes are similar, so we know what our zoom factor or what our ratio of sides is. Now be very careful here. In the table, we have a zoom factor of small figure divided by large figure, okay? So in this case, our small figure was 3 and our large figure was 9. It is a-okay to flip the numbers. So we would have 1/3. So the small figure could be written here. Look at the table. 3 divided by 9. This is small figure to large figure, okay? It means we're getting bigger. It means we're getting bigger. If we flipped it, it means we're getting smaller. So whichever number you put on top, that's the direction that you're changing the shape in. So the smaller number on top means you're getting bigger. If the smaller number was on the bottom, it means you're getting smaller. Let's take a look at the perimeters now. Now, hopefully I won't have to review perimeter. I believe it's pretty straightforward. I think you've covered it a lot in elementary and middle schools. But just a quick recap, just in case. Perimeter means adding all the sides together. So if we add all the sides of the small figure, say we were getting, erase this, 3 plus 4 plus 3 plus 4, which gives us 8 plus 6, which gives us 14. So we have 14 as our perimeter. Now, let's do the same thing for the large. 12 plus 12 plus 9 plus 9. That's 24 plus 18. And that ultimately ends up being 42. Okay? So perimeter for the large shape is 42. So in our table, we'll go up here, and for the small figure, we'll put 14. And for the big figure, we'll put 42. The ratio of perimeters. Remember, a ratio is a number being divided by another. In this case, we're going 14 divided by 42. So if I go and grab my calculator, 14 divided by 42. Now, you could use your calculator. I could have gone and grabbed my calculator. But typically when we're talking about ratios, it's a little bit easier if you keep it as a fraction. So what we should do is we should reduce the fraction as much as possible. So I'm going to erase this. And redraw it up here. 9, 9, 12, 12. The ratio of the perimeters in this case would be this. 14 divided by 42. In order to simplify the fraction, we need to divide by a common number. In this case, we can divide by 2. So I'll divide by 2. And that's going to give me 7 divided by 21. Now, we can also continue further and divide by 7, because 7 is a common term. So 7 divided by each number is going to give us 1/3. So our ratio of perimeters is going to be 1/3. Okay? Now, if we were comparing, let's say we were comparing our ratio of sides to the ratio of perimeters. Initially, you might look at these two numbers and you'll be like, yeah, they're pretty different. They're different. But not really. Because in one case, this case right here, we simplified. We simplified. But over here, we haven't. Watch what happens when we simplify that number. We take 3 divided by 9. A common number between them is 3. So we divide 3 on top and bottom, and we get 1/3. So really, this isn't 3/9. This is simplified as 1/3. So let's fix that. 1/3. So notice what you can see here. The ratio of sides is the same as the ratio of perimeters. The zoom factor is the same as the ratio of perimeters. They are 1-to-1 pretty much, okay? Earlier, we calculated the area. So if you remember, we calculated the area of each of these. We got 12. We got 12 for the small figure and 108 for the large figure. Let's add that to our drawing here. We have 12 and 108. Now, Again, we're going to calculate a ratio. So let's try that again. 12 divided by 108 equals, let's simplify. Divide both of them by 2. We get 6 over 56. Or I'm sorry, 54. We can simplify further by dividing by 2. And we get 3 over 27. Can I simplify even further than that? Sure, we can divide by 3. And that gives you 1 over 9. That is our simplified ratio of areas. So this is what's going here, 1 over 9. So what you can tell here, the ratio of the sides and the ratio of perimeters is the same. It is the same. However, the ratio of sides and ratio of areas is different. The ratio of sides to ratio of areas looks like this. For the ratio of sides, ROS, and ratio of areas, ROA, we have 1/3 and we have 1/9. Now recall that the zoom factor is R, okay? That is our ratio of sides. And area factor was R squared. So in this case, it makes sense that we have 1/3 and 1/9. The reason for that is if we square this, we get 1/3 times 1/3, which equals 1/9. That makes sense. So the ratio of sides and ratio of areas are related, okay? The ratio of sides is R, the ratio of areas is R squared. The ratio of perimeters, the factor by which the perimeter increases is the same. So, for example, let's say I had the perimeter of 14 and the perimeter of 42 for these two shapes. I know that the small shape has a perimeter of 14 over here, right here. Okay? And I know the perimeter of the larger shape, P equals 42. If we were to compare them, they should be 1/3 of each other. So, let's say I took my 42 and I multiplied it by 1/3. I should get 14. If I divide that, 42 divided by 3, I get 14. So, as you can see, the ratio of sides, ratio of perimeters, and ratio of areas have a relationship. The ratio of sides, ratio of perimeters are the same, but the ratio of sides to the ratio of area is R squared, is by R squared, okay? All right. Also, to keep in mind, if you're putting the big number on top, you are going from a bigger shape to a smaller shape. If you put the bigger number on the bottom, you are going from a smaller shape to a bigger shape. So remember, if the bigger number that you're putting, say this one, if the bigger number is on the bottom, you're going from a bigger shape to a smaller shape. If it was flipped around, you're still comparing similar figures, but you're doing it in reverse. You're going from small to big. And the way you can check that is when you multiply by 1/3 or you flip the numbers and multiply by 3, if you're getting a bigger number, you're going from small to big. If you're getting a smaller number, you're probably going from big to small. So keep that in mind. Okay, so what I'd like you to do now, I'd like you to do some practice. So try these and see how you do. Right here. So I want you to try these problems. Okay? These are 3 pairs of similar shapes. They are all similar. What you're going to try and do is complete a table similar to this one for each set. So you're going to have an A, you're going to have a B, and you're going to have a C. Try your best, pause the video now, work through these, and then if you need to check your answers, move on. So pause the video now. Okay, so you should have worked through these problems. If you haven't, give it another shot, or if you feel like you've done enough, let's go ahead and work through them. I'm not going to work through A. A is very similar to 2 of the other examples I did, so I will go through B and C. If you're confused on A, go back and look at the other examples. So let's talk about B. So for B, this is what we have. B, we have 2 triangles. One is rotated and one is straight up. So if I re-rotate them, I can write them like this. I have a triangle like this and a triangle like this. I have a 6 here, a 4 here, 60, 60, 90, 90, and these have to be 30. Interior angle sum theorem, 180 minus 60 minus 90 is 30. Now, if I want to solve this, and I'm going to go through this quick because you have plenty of experience with this, I want to find the missing sides. So let's start with this h over here. I'm going to use law of sines. So law of sines is sine of A over A, sine of B over B, sine of C over C. So in this case, I'll go sine of 90 over h equals sine of 30 over 6. Then I'll cross multiply and I get 6 sine 90 equals h sine 30. Divide both sides by sine 30. Sine 30. And ultimately I should get that h equals 12. So now I know that this h equals 12. Now, let's go ahead and find some of the other lengths. So I'll erase this. If it lets me. Let's go ahead and find this length here. I'm going to call this A right here. So if I was solving for A, I'll do the same thing. Sine of 30 over A equals sine of 90 over 4. Cross multiply. 4 sine 30 equals A sine 90. Divide both sides by 90. Sine 90, sorry. And I have that A equals 2. So now I know that A equals 2. Erase some more, because I love erasing. Ha ha ha. Let's go ahead and find the last value. So you could use Pythagorean theorem here, you could use anything you wanted. I'll just continue with law of sines. So I'm going to call this one b up here. So sine 60 over b equals sine 30 over 2. 2 sine 60 equals b sine 30. Divide both sides by sine 30. And I have b equals 2 sine 60 divided by sine 30. 2 root 3. Now, if you're used to radicals, this is a very clean way to write this. You can just write this as 2 root 3. If you wanted to do decimals, it would be 3.46 is about what b is. Either or, no problem. So I'm going to write this as 2 root 3, but you could write that as anything you wanted. You could do, well, not anything you wanted. You could make it a radical or you could make it a decimal. All right, so now if we look at our triangles here, we'll notice something. If I redraw it, I now have a triangle with a side length of 12 and 6, and a triangle with a side length of 4 and 2 and 2 root 3. If I find the last one, okay, we can then search for the zoom factor. So let's find this last one over here. I'll call this one C. Sine of 60 over C equals sine of 90 over 12. 12 sine 60 equals C sine 90. Divide both sides by sine 90. And I get 6 root 3. 6 root 3 equals C. And if you were rounding, that would be 6 root 3, about 10.4. So you would have gotten 10.4 if you were rounding for C, and you would have gotten 2 root 3, 3.5, or 3.46 for B. All right. Once again, I'm just going to keep it in root form because it's a much cleaner way to do it and it's more exact. When you round, there's a little bit of rounding error. So I'm going to stick with this 6 root 3 right here. 6 root 3. Now, I can erase this, and this is 6 root 3. If I start dividing things, we can find the zoom factor or the linear scale factor. So let me go ahead and work through that for you. Here you are, as soon as I get this gone. Okay, if I'm searching for this, I can go like this. 12 divided by 4 is 3. 12 divided by 4 is 3. 6 divided by 2 is 3. And 6 root 3 divided by 2 root 3. Same on top, same on the bottom, cancels. So I have 6 divided by 2, which is also 3. So our zoom factor here is 3. And remember, the zoom factor is the same as the ratio of the corresponding sides, which is the same as the linear scale factor. So if you had your table, this one, like this, our ratio of the sides would be 3. So our ratio of the sides would be either 3 or 1 over 3, depending on what's on top. So in this case, the small figure is on top, so we're putting the 1 on top. So we have 1 divided by 3. Our perimeter of the small figure, add them all up. The small one is 4 plus 2 plus 2 root 3. And I get approximately 9.46. Let's try the bigger figure. 6 root 3 plus 12 plus 6. It's about 28.4. Our ratio of the perimeters is 9.46 divided by 28.4. You can't really simplify it because they're decimals. You get about 0.33. Now, I'm going to go ahead and jump ahead by calculating area. Area is 1/2 base times height. I'm going to go ahead and calculate it without showing you. I trust that you recognize that this is the height and this is the base, okay? So, 6 root 3 times 6 divided by 2 is about 31.18. 31.18. And actually that's for the bigger figure, sorry. 31.18. For the last one, for the smaller one, we have 2 root 3 times 2 divided by 2 is about 3.46. 3.46. All right. Now, let's take the ratio. 3.46 divided by 31.18 is approximately 0.11. Now remember that the ratio of sides is related to the ratio of areas by squaring. So let's just check that. What is 1/3 squared? It's 1/3 times 1/3, which is 1/9. And 1/9 is 1 divided by 9 is about 0.1, which is about this. Also, notice that our ratio of the sides and the ratio of perimeters are also the same, because 1 divided by 3 is 0.33. So what we determined in the example and what we found in part B is that the ratio of the sides, ratio of perimeters, and ratio of areas are similar relationships for any shape. It doesn't matter if it's a rectangle, a hexagon, a thingy, anything like that. As long as they're similar, this relationship is true. Ratio of sides, ratio of perimeter, same. Ratio of sides to ratio of areas by a square. Okay, square value. All right, I'm not going to go and solve C. If you have specific questions about C, please let me know. The video is getting a little long, that's why. So, yes, please let me know if you have questions about C. We're going to be practicing some story problems in class. I might make a video about story problems later, but I think you'll have sufficient practice in class for those. Okay, thanks for watching the video today. Remember, perimeter, area, ratio of sides, zoom factor, similarity. That's what all of this is about. All right, thanks for watching. Have a good day.